Well, dear students, today we will be discussing the interpretation of Powerlab graph tracing. This is very important, especially in the new drug development. We already covered this in the TAT courses, you see, at your MPhil or PhD level. So, important to understand is that, for example, if I recall your memory regarding the new drug development, and new drug development is a convergence of different disciplines, you see, involving the pharmacokinetics, pharmacodynamics, physiology, biochemistry, and metabolism. You see, combinatorial chemistry, synthetic chemistry, and consequently, if I simplify it for you, so the new drug development have a preclinical phase and a clinical phase. Clinical phase is in the humans, and the preclinical phase is being carried out in the experimental animals. We determine the toxicity study and, of course, the pharmacological screening, then pharmacokinetics and dosimetry in preclinical phase, whereas in clinical phase, we translate the basic research into clinical practices, which is not the domain of this lecture. Now, important point to understand here, for example, we have developed, rather our research group has developed different flavonoids, and F9 is one of that which has been targeted to one of our students for the possible pharmacological screening. And what we did that for the possible relaxant activity on isolated rapid jet general preparation, you see, and here you can see this is the control response, and this is the height of control response, you see, and then A is the concentration of this molecule goes on. So at 5 microgram, the relaxant activity has been started, and it is very prominent at 15 microgram, and you see in 20 microgram. And once we plot that values, you see in the graph prism, so you get a graph like this one, and this response is as percent of the control response, you see, and this is what we have already discussed in the laboratory. Regarding this, you see, this is the 50% response, and concentration is on x-axis. So at this mean curve, you see, if you drop a perpendicular, and it's going to touch this concentration on the x-axis. So this is the EC50 value, you see, and this is already discussed with you. When relaxant activities and rapid general preparation is there, then we test it in the presence of high molar potassium chloride induced contraction, especially the 80 millimolar potassium chloride induced contraction. And if it is relaxed, it means that the molecule is potentially having a voltage gated calcium channel blocking inhibiting activity. This is the baseline, if you see, if I carry it to you, and here again this is the control response. I mean the response, the height and amplitude of this, especially potassium chloride induced contraction, that is preceding, even before the start of the dose response, you see, and then it's going to have a relaxant effect on 15 and 20 microgram per ml, and again you get a graph like this one. Remember, this is on potassium chloride induced contraction, and you can see here again this is the EC50 value. And this is again plotted as percent of control response, and control here is this region. So we have discussed that. We are not going to spend much more time on this. Now, since the molecule is having possibly voltage gated channel inhibitory response, how? That's because the studies tells us that if a molecule is having a relaxant response and high molar potassium chloride induced contraction, so it is expected to have a voltage gated calcium channel blocking activity. So what we do, first we suspend the tissue, then stabilize its response, then we treat in the K-normal, K-normal solution, and then you get a curve like it depolarizes. Then we treat with the KRH tyrrhode solution until this process is repeated 2 to 3 times, and the tissue is decalcified. Now this is a decalcified tissue. There is no pendular movement here, and this is a straight curve. But remember, oxygen supply is still to the tissue. Where is the tissue? The tissue is being suspended in the organ bath, you see, and it has oxygen supply. It has nutrient thyroid solutions. You see, here is, for example, this is carriage, and then normal carriage, and it's repeated 2 or 3 times, and this pendular movement is lost, so it is now a decalcified tissue, and this decalcified tissue is to be recalcified. It has to be what you can say, if I write it for here, recalcification. Now we will do recalcification. So if we are going to do recalcification, this will be with a standard known concentration. For example, 1 into 10 raised to the power minus 4 molar, then 2 into 10 raised to the power minus 4 molar, then 8 into 10 raised to the power minus 4 molar, until on you multiply this double. 8 multiplied by 2 means 16, 16 multiplied by 2 mean 32, 32 multiplied by 2 mean 64, and then with a 168, and then 256, you see, and carry on until you get a curve. And remember, this is without drugs. So this process is repeated twice. This is a control curve, and this is repeated twice until you get another curve. You see, again decalcified, and you have to recalcify it like this one again. And now what then you will perform a wash, and once you wash it, you see, you will again carriage normal. And what you do, so if I carry for you this here, then you give what you can say, for example, 5 microgram per ml relaxing activity was there, so you add 5 microgram of the F9, 5 microgram per ml final bath solution of F9 molecule to this tissue already being suspended here. So you see, and then give an incubation period of 1 hour, and again you have to recalcify the tissue, apply the same amount of calcium, you see here, and you will get again a response like this one. So at the end of the day, at the end of the experiment, what you will get a response or a graph response like this one. You can see this is a control response. Then in the presence of 5 microgram per F9 per ml, that's F9 molecule, and then you repeat it with till. So this is the control response. Control mean without drug, without F9. And remember, if there are some channels are blocked, some channels, voltage gated calcium channels are blocked by F9. So what will happen? The calcium from this solution, you see, won't be able to enter to these tissues. And if these calcium channels are blocked by the F9, so what will happen? Sufficient amount of calcium won't be able to get enter into the tissue, and a response of this much amplitude is not being attained. This is control response, and in the presence of 5 microgram per ml, you see what will happen. In the presence of 5 microgram per ml, this much response of amplitude is not gained. It's difficult for this in the presence of 5 microgram to reach the height of control. So it means some voltage gated calcium channels are blocked. Because why? Because once we recalcify it and going to recalcify it, so the calcium has to enter through the voltage gated calcium channel or the ion exchange channel. You see, this is actually determined mechanism, already a standardized mechanism. So important to understand in this mechanism here, you see these are the control curves, 1 into 10 till you reach 256 into 10 to the power minus 4 molar response. And here this is the spontaneous rapid unit preparation. Then you wash with K-normal, again K-normal carriage 3 times, and this is, for example, a baseline, you see. So in the presence of without drugs, you see this is control curve, and in the presence of 5 microgram this F9 molecule, you see. So what happens? once you recalcify with this amount of calcium, so it is not going to reach of similar amplitude. If I draw a dash line, so this much amplitude is being not attained. And in the presence of 10 microgram, again, and you give an incubation period of 1 hour, you see what happens. You see, this is a very less amount. There's less amount, mean less, a very less. More channels are blocked, and it's not going to reach the height is gained by the control. So if I club this curve, and this curve together, so you will get a curve like this one. You see, this is control of a bit lower amplitude with a 5 microgram and much lower amplitude with 10 microgram. You see, this is with 5 microgram, and this is control curve. So if we proceed for you, what happens? You see, these are the graph tracing of one of our MPhil students. You see, and these are the normal control response. This is in the presence of 5 microgram for F9 molecule, and this is in the presence of 10 microgram. And a very interesting is, these are the curves when we plot this in the graph transducer. This is control, blue is the control, and this is in the presence of 5 microgram, you see, and this is in the presence of F9 molecule in the presence of 10 microgram. So these are being plotted in the graph prism, and you get a graph like this one. Very interestingly, remember, here is the log value of the calcium, and this calcium value, you see, 1 into 10 raised to the power minus 4 is being expressed as log values, and these log values, you see how it's converted. This is for your understanding. You see, 1 into 10 raised to the power minus 4 is expressed in decimal points expression, and then it is expressed as converted in the Excel sheet as a log 10 expression, and here is this value. So we have plotted this log values here on the x-axis, mean the concentration of the calcium, and response is plotted on the y-axis. So you will get a curve like this one. Most important is, you see, dear students, similar type of curves are drawn for the verapamil, a standard calcium channel blocker in the presence of 0.03 micromolar and 0.1 micromolar. And you see, like verapamil, this is the control response, and this is the EC50 value. Here, for example, minus 2.5 log mole calcium molar, and this is the EC50 values, somewhat between 1.5 and minus 0.5 for the in the presence of 0.03 micromolar of verapamil. And in case of 1 micromolar verapamil, we cannot calculate the EC50 because there is no sufficient amplitude of the calcium concentration response curve. So consequently, we were not able to calculate or draw an EC50 value for this one, especially for 0.1 micromolar of verapamil. Similarly, a right shift here by F9 is observed here, and the right shift in the EC50 of the F9 resemble the right shift of the EC50 of verapamil here, and then we can say that it's going to have a calcium channel blocking activity. Regarding the graph prism data, dear students, let me share with you some graph prism data, and that will be in this case, for example, we have already opened some prism file, and this is the spontaneous graph prism file. And if I carry to the data, this is in 1, this is in 1, this is in 1, this is in 2, you see, this is in 2, and this is in 3, and here that is the concentration of this F9 molecule, and you will get a graph like this one. This is already plotted. And regarding the what you can say on the verapamil values, you see, especially the F9 molecule, this is control response, this is the what you can see, the log calcium molar, and then this is the in 1, this is in 2, this is in 3, and you see in the presence of F9 flavonoid number 9 molecule of 5 microgram per ml. This is in 1 value, in 2, in 3, and same is the value for 10 microgram per ml of the F9 molecule, and consequently you see you get a graph like this one, for even for verapamil like that one. So what is important to understand is that at least you should have a plotted table of figure of this, especially in the graph prism, and then you calculate the EC50 values and put all these values, especially in the graph prism. That can help you. So F9 molecule, there is a right shift from the control to from control curve to that of F9 in the presence of 5 microgram per ml, which resemble the curve of what you can say verapamil, a calcium channel blocking drug. So important is that I hope now you understand all these things. Okay?